algebraic limits are pretty easy. I think a lot of calculus classes start off with algebraic limits because really if you can substitute, you can evaluate. I guess in my mind the problem is if you're not thinking about continuity, you don't really know what you're doing and you're focused on getting the number at the end. And maybe that'll be true anyway. So algebraic limits rely on continuity. So you need to use the calculus definition of continuity, or at least that's what's going on in our head. So let's review. F is x squared when x is less than 2. So a parabola, and I guess we know that parabola. Ew. I don't know why this always reverts to red. Okay. Anyways, so for x is less than 2, we have some parabola. And for x is greater than 2, we have some version of x cubed. And our job is to find that constant multiplier, that coefficient, to make everything match. In fact, we have a nice visual here that I made. Okay. Right, so really, we have x cubed for x is less than 2, x cubed for x is greater than 2, and we can move things around. So, like, our job is to make... Oh, there it was. Our job is to make these connect, make it have a continuous graph, even though it looks like we're not going to have something that's differentiable. But that's okay. So we should start off with the definition of continuity, and that is, well, if f is continuous at x equals 2, the limit as x approaches 2 from the left of f should be equal to f of 2 is equal to the limit as x approaches 2 from the right of f. I mean, you might be thinking, why don't we use the limit as x approaches 2 from both sides of f equals f of 2, because that's also the definition of continuity. And the answer is, well, we're going to have to break this apart to the left and right hand side of 2, since we're talking about, well, this particular version, this piecewise defined function. And so let's rewrite, for x values approaching 2 on the left, 1.9, 1.99, 1.999, we'd be putting those into x squared. So we can say the limit as x approaches 2 from the left of f is the same as the limit as x approaches 2 from the left of x squared. And then f of 2, well, looking at this domain here, when x is equal to 2, we use 2x, or ax cubed, so we're going to write a times 2 cubed. And the limit as x approaches 2 from the right, numbers like 2.1, 2.01, 2.001, those would be going into ax cubed. Now, turns out x squared and ax cubed are continuous, so we're kind of relying on continuity to prove continuity, because I don't feel like doing a numeric limit. But you should know, numbers near 2 into x squared are going to give us 4, 2 squared. A times 2 cubed is 8a, and likewise, numbers really close to 2, 2.1, 2.01, 2.001 into ax cubed are going to give us 8a. So we have this three-part equality, and we can see 8a and 8a are the same, so we might as well combine and get a equals 1/2. All right, so when a equals 1, and we don't really need to write a conclusion that when a equals 1/2, f is continuous at 2, because we started off with that definition. I think this is nice and pretty. So I guess the important part here is that, well, we knew f was continuous, which allowed us to substitute. And so what we're going to do is we're going to use continuity to not have to actually do limits. We're going to evaluate limits algebraically, which really just feels like algebra, but if you're doing algebra, you're not doing calculus. So I think it's supposed to look like algebra, but we're not really doing algebra. And so here's the overview. If a function has a removable discontinuity, we're going to remove it. Then we can use continuity to get the limit without following the limiting process, meaning not using numbers closer and closer to that input. So if you're not thinking about continuity here, you are going to be confusing algebra with calculus. Now again, it's going to look the same, but we're not really doing calculus. Okay, so we're going to evaluate the limit as x approaches 2 of x squared minus 4 over x plus 2. I guess we could sketch that, and maybe we should. But the important thing here is that this graph is undefined at -2. This graph has, oh no, that's not a vertical asymptote, is it? We should factor harder. So let's rewrite that as x minus 2 times x plus 2 over x plus 2. So this is basically the graph of y minus 2, except for it has a hole. It has a removable discontinuity at x equals -2. Now the thing is, we're asking, well, what's the limit as x approaches 2? Way over here. And that should be really easy because we're talking about a part of this graph that's continuous. And so because x squared minus 4 over x plus 2 is continuous at 2, we can just substitute. Because for lack of a better phrase, I don't want to use f here, but it is. Let's get rid of that for a second. What's the definition of continuity at a point? My pen is dead. Well, that happens more than it doesn't. The definition of continuity at a point is limit as x approaches to, well, let's do it in this case. Limit as x approaches c of f of x is equal to f of c, meaning the y value is equal to the limit. So what we're really doing here is instead of doing the limit, we did the y value. And that's pretty nice. So here we already had that graph. We know we're looking at a line with a removable discontinuity at -2. Oh, at 2. Sorry, I thought I switched the x, but no, I switched the x minus 2. And so again, maybe we think about this graph of y is equal to x plus 2, x minus 2 over x minus 2. And this is a graph, basically the line of y equals x plus 2. It just has a hole at x equals 2. And you can see clearly 2 is not in the domain of x squared minus 4 over x minus 2. Okay, so we shouldn't write 0 over 0, but we should always be thinking. So you should always check for continuity, and when you substitute 2 into the denominator, we get 0. But you also want to substitute 2 into the numerator. We get 0. Obviously, 4 minus 4 is 0. Because that 0 over 0, there's a name for that. It's called it's one of many. I can't spell. Determinate form. And, you know, that means exactly what it sounds like. In this form, we cannot determine what the limit is. Sometimes 0 over 0 is 4, like it's going to be in this case. Sometimes 0 over 0 is 1. Sometimes 0 over 0 gives us a limit that does not exist. All kinds of different things, right? We don't write that down, but we should always check. Okay, anyways, so once we factor, we get the limit. Don't forget to write the limit as x approaches 2 out front. We're always going to write that as long as we have x's. X minus 2 times x plus 2 over x minus 2. Now, another bit of knowledge here, you know, if we were doing a numeric limit, we would be inputting values like 2.1, 2.01, 2.001 into all the x's. And so I think instead of canceling, a better way to think of this is, well, if you did 2.1 minus 2 over 2.1 minus 2, that would be 1. That's kind of a waste of time. Likewise, if we put in 2.01 minus 2, 2.01 minus 2 in the denominator, that's going to be 1. So whenever we'd be doing a limit as x approaches 2, those x minus 2's are irrelevant. We might as well just do the limit as x approaches 2 of x plus 2. Now the cool part is x plus 2, that's a continuous function. So notice in between here, we removed the discontinuity. And since x plus 2 is continuous, I'm going to have my students in class write that for now, because if you're always writing that, eventually you'll always be thinking about continuity. We can use the definition of continuity, and instead of doing the limit, we get the y value. We just substitute. 2 plus 2 is 4. Hopefully we're getting that. All right, let's try it again. So the limit as x approaches 1 of x cubed minus 1 over x minus 1. Well, what are we going to get? Maybe we sketch again. So y is equal to x minus 1 times x squared plus x plus 1 over x minus 1. So we're going to get a parabola. I'm not sure if this crosses the x-axis. I don't think it does. Anyways, we're going to get a parabola with a removable discontinuity at x equals 1. To me, if you remember all your pre-calculus stuff, this graph pretty obviously has a hole at x equals 1. Okay, let's get rid of that. So when we substitute in 1, we get 0 over 0. And again, you got to substitute numerator and denominator. You're doing this in your head anyways. So once we factor, like you saw, we're doing that whether we're sketching or whether we're just doing the limit, we get an x minus 1 in the numerator, x minus 1 in the denominator. And we're going to ignore those. And the reason we're going to ignore them is if I do 0.9 minus 1 over 0.9 minus 1, we know that's going to be 1. And, likewise, if we put 1.1 minus 1, 1.1 minus 1 in the denominator, that's going to be a 1. For any x value near 1, the x minus 1s are going to divide to be 1. So we might as well do an easier limit that's going to have the same result. And that's the limit as x approaches 1 of x squared plus x plus 1. Now, x squared plus x plus 1, that is continuous, which means we can use that definition of continuity, substitute 1, instead of actually doing that limit process, and we just get 3. Which means I guess my sketch was wrong. The vertex must have been to the left of the y-axis. Whatever. Okay, let's do this without a sketch. Now, if you're looking back as review, this should be obviously a derivative, but you may not realize that right now, because this 1 is actually also the square root of 1. If you pretend the x's are h's, maybe you'll see it, but whatever. So, when we substitute, we get 0 plus 1 in that square root, so 1 minus 1 in the numerator, and 0 in the denominator, which means we have a removable discontinuity. Now, let's look back for a second. Right here, this pair of x minus 1s created the removable discontinuity. When we put 1 into x minus 1, we get a 0. So we knew that when we substituted and got 0 over 0, there's an x minus 1 in the numerator, there's an x minus 1 in the denominator. Back to the problem before that. What created the 0 over 0 here? Well, we're substituting in 2, so it was the x minus 2 over x minus 2. Which means in this case, obviously the x in the denominator is creating the 0 in the denominator, but the structure we want to get to, what we're going to aim at is, we're going to get the limit as x approaches 0 of x times some stuff in the numerator, x times some other stuff in the denominator, and then we're going to ignore those x's, and hopefully what's left will be continuous. That's the plan. Okay, so how in the heck are we going to get rid of that square root? Because we can't square the square root, we don't even have an equation. And the answer is we're going to multiply by the conjugate, square root of x plus 1 plus 1. Obviously over itself, because here, really what we're doing is multiplying by 1. So, the square root of x plus 1 times another square root of x plus 1 is just x plus 1. And we get a positive square root of x plus 1, a negative square root of x plus 1, which add to 0. And then negative 1 times positive 1 is this minus 1 here. Now in the denominator, remember where we're going. So we want to keep this x by itself because we want to remove that discontinuity. Okay. So pretty clearly, easy algebra in the numerator. We can subtract 1 and we just get x. And so now notice as x approaches 0, 0.1 over 0.1 is going to be 1. Negative 0.1 over negative 0.1 is 1. Negative 0.01 over negative 0.01 is 1. We don't need that pair of x's. So we'll just ignore them and do another limit that has those x's removed. Now 1 over the square root of x plus 1, that is continuous at 0. So we can just substitute and get 1 over 2. Oh, I guess I didn't simplify. But I don't know, you don't really have to simplify anyways. All right, let's see. Do we need some more examples? Yeah, I think so, just to practice the algebra. Okay, so this is just so stinking ugly, but it's going to be good practice for doing formal limits. So when you substitute 0 in the numerator, we get 0. Okay. When we substitute 0 into the denominator, we get 1/6 minus 1/6 is another 0. And what that means is there's a removable discontinuity for us to find. And what structure are we going to try to find? Well, it's going to be x times some stuff in the numerator, x times some stuff in the denominator. And how do I know that? Well, x is the factor that I substitute 0 into to get 0 over 0. You know, if it was limit as x approaches 4, I'd be looking to remove an x minus 4 over an x minus 4. Okay. So there are a lot of good ways to go. I think the quickest is to just get rid of all the denominators. I know a common thing is, hey, I will get a common denominator between the 1/6 and the 1 over x minus 6, and then I'll multiply by the reciprocal. Totally works. Go for it. This is just a little bit quicker. So if I multiply the denominator by 6, this 1 over 6 turns into 1. If I multiply the denominator by x minus 6, this 1 over x minus 6 turns into 1. So I just multiply by both of those at the same time. So 1 over 6 times all this junk becomes x minus 6. 1 over x minus 6 times all this junk, well, the x minus 6's divide, and I just get a 6. So I get x minus 6 plus 6. And in the numerator, we have multiplication, so we're not going to distribute that out. And you can see if you substituted 0 now, we actually still get 0 over 0. So we will simplify the denominator. Negative 6 plus 6 is 0. And now we're making progress here, because 6x over x, well, if I put in numbers near 0 like 0.1, 0.1 over 0.1 is 1. 0.01 over 0.01 is 1. That's kind of stupid. I don't want to do that limit. I'll do another limit where I'm not constantly getting this pair of 1s. 6 times x minus 6. Now 6 times x minus 6 is continuous, so I can substitute 0 instead of doing the limit, using that definition of continuity, and just get 36. So hopefully that's enough examples. I guess if you're in class with me, you can tell me there are more, but you're not, so we're done.